Hello, gentlemen. Welcome to our video on 15.3 called Understanding Equilibrium Constants. Now, thus far, we've talked about how to write equilibrium expressions and what equilibrium is, but we haven't paid much attention to what those constants actually mean. So this video is to help clarify that. We're looking at two major things: the magnitude of the equilibrium constant and how the constant can change as you change the equations or elementary reactions. So the first thing is magnitude of your elementary reactions. So we're looking at magnitude. We're going to use the example of the production of phosgene. Now phosgene, if you remember, is this substance here, COCl2. It was first introduced back in chapter 10 when we talked about chemical warfare during World War I. It was a chemical agent that was used to end the stalemates that were happening in the trenches. So that's not our focus today, but this is the substance and this is how it's produced. Now, our major focus today is to realize that it is produced from carbon monoxide and chlorine gas. Those are my reactants. It's produced into phosgene, and those phosgene particles, they collide together and then they go back to chlorine gas and carbon dioxide. And they happen back and forth until the rates of production and decomposition are equal. That is when they reach equilibrium. Once that happens, we can write an equilibrium expression. So the equilibrium expression, we'll do it in terms of concentration. I could do it in terms of pressure as well, but I'm just choosing concentration here. It's a little more common. So the format is the concentration of your products over the concentration of your reactants. So in this particular case, my product is phosgene. Now, if I were to have some kind of, coefficient here, then I would put it here as a superscript. I'll put 1 here. Traditionally, we don't have to put 1, obviously. If things are in a 1-to-1-to-1 relationship as they are here, these are all 1. So there's really no need for any coefficients. Any superscripts, excuse me. But if you had anything else there, you'd put them as superscripts. And I know last chapter we said that was a no-no. You couldn't take your balanced chemical equation coefficients and put them as superscripts here. But this is something a little bit different. We're comparing products to reactants. This is not a rate law, so to speak. I know it's a combination of two rate laws, but when you combine them and talk about equilibrium, you can then take them for their relational, balance here, these coefficients. And also you can do it if it's a single step reaction. Right now we're assuming it's a single step reaction, so the coefficients in the balanced chemical equation are the superscripts. So we can do that in this chapter, so please do. All right, now if we were to do this, we would get that the equilibrium constant is 4.56 times 10 to the 9th. Now this is done experimentally to figure this out. Now, in last chapter, the K values, it was important to note the units because the units told you a lot about the rate law and the orders of reaction or the molecularity. In this chapter, we don't really care as much about the units here, so you can leave it unitless. We care about the magnitude, how big or small this is. Now, this is a pretty large number. 10 to the 9th suggests that this is significantly greater than 1. It's really large. So that means that the numerator must be pretty darn large in comparison to the denominator to give you such a large number. That says a lot about what's happening in the chemistry in that flask here. So, down here, a large K sub C or K sub P means that the concentration of my product in this case, phosgene, which is the numerator, must be much larger than the concentrations of carbon monoxide and the concentrations of chlorine gas, which are the denominator. So what this is saying is that the forward reaction going from carbon monoxide and chlorine gas this way, that forward reaction, highlighted by the red arrow there, is dominant. And the production of my product phosgene is going to be favored. So in a question, if it said which direction is more favored, the forward direction or reverse direction, you look at the equilibrium constant being so large here to the 9th power and say, well, the products are dominating here. They're being produced in greater concentrations overall at the end of this reaction cycle, or once it hit equilibrium. On its way to equilibrium, the product is being formed more readily. Okay, and a short way to say that is we can say equilibrium lies to the right, as I have here in yellow. So equilibrium lies to the right, meaning as you're going towards equilibrium, you have your initial reaction, you put things in the flask, they start to react, and as they go to reach equilibrium, where the rates of the forward and reverse reactions are the same, you're going to produce more product along the way. So the equilibrium of the equilibrium lies to the right, meaning the product is produced more readily. Okay, now to speed things up, the opposite would be true if this were smaller. So if it was 10 to the negative 9th, that means your denominator is larger and the equilibrium lies to the left. And that's what's here in blue. So if K is much smaller than 1, equilibrium lies to the left, and your reactants are dominant, the reverse reactions favored. And as I said earlier, if equilibrium lies to the right, that means your K is greater than 1, equilibrium lies to the right, products are favored, they're dominant. The forward reaction is what's going to be dominant in that reaction. Okay, that's magnitude. Now, the equilibrium constant can change as you go through different mathematical processes or different procedures, whatnot. And here are the things you can do. You can flip the equation, you can add elementary reactions, you can multiply by coefficients. Now we've done all of these things in chapter 5. When you flipped a reaction in chapter 5, we talked about enthalpy. The enthalpy flipped its sign. So if it was exothermic and you flipped the reaction, it then became endothermic and became positive. Adding elementary reactions, when you use Hess's law in chapter 5, when you added up all the elementary reactions, you added up the enthalpy values. And when you multiply equations by coefficient in chapter 5, if you multiply the entire equation, so let's say it was A plus B goes to C, if you multiply everything by 3, then you would take your delta H and multiply that by 3 as well. Now, we're going to be doing something similar to that. We're not doing the exact same things that we did in chapter 5. However, it's going to be very familiar to you if you think about chapter 5 when we're doing this process. Okay, so the first thing, flipping the equation. Let's say I had a sample equation. A plus B goes to C plus D, and they've gone to equilibrium. And this has some K value, we'll call it, its K is K sub 1. If I flip it, C plus D goes to A plus B. What you do with this K value is the new K. We'll call it, K sub 2. This new K, K sub 2, for this flipped reaction is going to be the reciprocal of your original one. So you just take K1 and put it under 1. So please write that down. If you flip a reaction, you take the reciprocal of the flipped reactions, or the original reactions, equilibrium constant. Now, if you're adding up elementary reactions. So let's say we have two elementary reactions. The first one, A plus B goes to C plus D. Again, it has a K sub 1 as its equilibrium constant. In the second elementary reaction, we have C plus F goes to G plus A. And this is going to be K sub 2. Now, if we're going to be doing some kind of, Hess's law kind of thing, and we're flipping these to get them to, things to cancel out and all, obviously these two would cancel, these two would cancel, and my net reaction would be B plus F goes to D plus G. So the new K for this one, we can call it K sub 3. It is not going to be adding up K1 and K2. In this case, when you're adding up elementary reactions, as we're doing here, you multiply your K values. You multiply your equilibrium constants from each step. So K1 times K2. And you get K3. Lastly, when you're multiplying, as I said earlier, change the equilibrium constants themselves by doing these three things. Children, take notes. Adios. An equation by coefficient. So let's say, again, we have A plus B goes to C plus D. That is K sub 1. If I were to multiply it, so I'll just draw it again. It's terrible arrows. If I multiplied everything, might want to give some space here. If I multiplied everything, let's say by some integer n. Back in chapter 5, we multiplied our enthalpy by n, if that were the case. In this chapter, we're not going to do that. If we do that, then I take my K sub 1. If I want to find the new K, which still say this is K2 for this reaction here. To find K2, I take my initial equilibrium constant, and I raise it to a power of that multiplier. So that n that I multiplied through becomes a multiplier there. All right, gentlemen, so please take note of the two major things that can happen with equilibrium constants. Their magnitudes can change, and know what that means. And then we can